Hi. Hi, everyone. My name is Julia Flament-Wallin. I'm an AI engineer and team lead at Capgemini. I have 9 years of experience in the intersection between data science and engineering, and I have an annoying habit of always asking, why is it like this? All right, so I'll preface this with the fact that I agreed to do this talk on very short notice, and I didn't have a talk ready, so I won't go super duper deep, but hopefully give an overview and maybe tie things together a little bit in terms of where we come from and where we're at. Maybe you don't agree with me, maybe I'm being super controversial. We'll see in the end if I'm successful at that. So what I would like to do is to take you through a very short history of the semantic web failure, ? The semantic technologies we have as a result of this effort, the rise of graph databases and knowledge graphs, as well as data mesh, the new architecture, data architecture paradigm, and what it might mean for data architecture in terms of possibilities for data science going forward. Okay, so we all know how Tim Berners-Lee invented the World Wide Web, not to be confused with the internet, in the late 80s. We all know this. I've even stood outside the very office where he worked at CERN in Switzerland. Shout out to Lilian Smestad for that. Anyway, it made the existing internet available and launched what we now might call Web 1.0 to the masses in the early 90s, 91. The read-only web. And as you know, the World Wide Web functions as an application layer protocol that is run on top of the internet, helping to make it more functional. A subset of you knows what Tim Berners-Lee's next contribution to the web was, namely the Semantic Web. In a TED Talk from 2009 called The Next Web, which Veronica Heimsbach watches every night before she goes to sleep, and 20 years since the invention of the World Wide Web, Tim introduced his new vision for the web. A web for open linked data that could do for numbers what the web did for words, pictures, video, unlock our data and reframe the way we use it together. This new vision resulted in millions, if not billions, of funds poured into a largely academic quest to create the semantic web, sometimes known as Web 3.0, which is an extension of the World Wide Web consortium, W3C, which is an extension of the World Wide Web through standards set by the World Wide Web consortium. The goal of the semantic web is to make internet data machine readable. Today, we're in the second decade of this effort, but we don't have the semantic web. The web that we all know and use every single day is not machine readable for the most part. When I'm planning a trip to France this summer, I must be the agent that first Googles flights, then train tickets to my final destination, and I have to make sure that my train doesn't leave before I can arrive at the station. There still has to be a human middleman or a middle woman or a middle non-binary to achieve this trip, because web pages are not, for the most part, machine readable, and I can't ask the machine to find flights and suitable train tickets unless there's a specific service for that. So what what do we have? 13 plus years and millions of dollars in research funds and pages upon pages of papers and standards and implementations since the inception of Web3. We have the Semantic Web stack. In order to implement the Semantic Web, we needed new technologies and standards to formally represent metadata. The semantic technologies we have as a result of this huge effort is the Semantic Web stack, also known as Semantic Web Cake or Semantic Web Layer Cake, and illustrates the architecture of the Semantic Web. The standard promotes common data formats like HTML, XML, etc. on the World Wide Web by encouraging the inclusion of semantic content in web pages. The Semantic Web aims at converting the current web, dominated by unstructured and semi-structured documents, into a web of data, introducing Resource Description Framework, aka RDF, as the foundation for the Semantic Web. Resource Description Framework, RDF, is a framework for creating statements in a form of so-called triples. It enables to represent information about resources in the form of graph. The Semantic Web is sometimes called giant global graph. Now you might say, okay, Julia, this is great, but what does it have to do with my database, my data warehouse, data lake, lakehouse, or platform? Well, the implementation of a RDF schema with the resource description framework is a graph. And this graph can be tossed in a graph database, for example. And this graph can be queried by the not so simple Sparkle language. There is an important distinction between what we call a graph database or property graph and a semantic graph or knowledge graph. I'll go a little bit into that. So, graph databases versus knowledge graphs. There is no standard property graph data model. So, each implementation of a property graph might somewhat differ. But in general, the property graph data model consists of 3 elements. There's nodes, the entities in the graph, edges, direct links, aka relationships between nodes, and properties, key value pairs that can be associated with either nodes or edges. There are several definitions of knowledge graphs, but here are a few that I like. A knowledge graph acquires and integrates information into an ontology and applies a reasoner to derive new knowledge. Or another definition is a knowledge graph is a knowledge base that uses a graph structured data model or topology to integrate knowledge and data. Knowledge graphs are often used to store interlinked descriptions of entities, real-world objects, events, situations, or abstract concepts, including their semantics. So the way I see it, in order for you to have a knowledge graph, not just a property graph, you need an ontology or a logical layer on top of your graph. Then there are some differences, like in a property graph, IDs are internal, in a knowledge graph, they're global, etc. We could go on, but I won't too much right now. Notice, though, a reasoner to derive new knowledge. This is something that I find extremely interesting and made possible as part of the Semantic Web stack with OWL and applications like Protege. So we talk about like finding patterns in data with machine learning, for example, right? Well, with an ontology, Imagine that you have node A with an edge to B, B with an edge to C, etc., and the ability to find business rules or just rules that no human defined or maybe noticed, but that can be derived just from facts about nodes and their relationship. So like in this example that I have up here, drivers are defined as persons that drive cars. We also know that drivers are adults. So all drivers must be adult persons. So just like a business rule that we can just find, no one has to define it. We can find it. Anyway, moving on. Here is an overview of just some of the available semantic graphs and property graphs at the moment. Yeah, quite a few popping up. Okay, so the Semantic Web effort gave us the Semantic Web stack, maybe also indirectly at least graph databases. Now, I just want to throw into the mix as well that perhaps just like parallel with the Semantic Web effort, we've seen implementation of graph theory and usage of graph technology to handle data in every huge web service, from Google to Facebook to Netflix, etc., in Web 2.0, by the way. So like, for example, Google search didn't put the entire internet into a ginormous relational database for them to query it with SQL and give us the result. No. It utilizes the power, speed, and flexibility of graphs. Meanwhile, again, during the last decade going on too, we've seen one enterprise after the other in any and every company, maybe but the tech companies or them as well, spend millions upon billions on huge migration projects, going from storing their business data and rules in relational databases on-prem to the cloud. And that's been great. It's massively simplified data storage for companies who doesn't really want to deal with data storage, at least not servers. And it has led to companies building their own data platforms, even going from selling whatever product it is that they're selling, for example, oil, to creating completely new products and services, even spin-off companies selling data as a product, looking at companies like, for example, Cognite. Still, modeling, for the most part, transforming and storing their data built on relational databases, so SQL, but now on someone else's computer, aka the cloud. Okay, so that's well and good. Can we just like let the FANG companies do their graph stuff and then everyone else use relational databases like normal people? I'm glad you ask. And like, let's be real. We all love a good Venn diagram, like this one, showing the intersection of things that killed Roman emperors and deodorants, like right guard. Some of us, not naming names, fell in love with logic, relational algebra, which underpins all relational databases, and SQL, and how it enables us to make beautiful logical data models. The problem is that business rules doesn't always fit into a matrix. And so in order to store and make use of data, sometimes the transformation of data in its original form to the contents of some database is a little bit like the process of fitting a circle into a square. And also the problem is that relational databases aren't very flexible. So this is something that any and every data engineer, or whatever you want to call it, has noticed every time they deal with hierarchical data. How do you neatly store this in a matrix? And don't say pivot table. Oh. New fields, the data model needs to be modified. company A required company B. Now their databases need to be merged somehow, or migrated and merged or something like that. Historical data and time series, not very elegant oftentimes. Duplicates, the need to represent and store a customer ID so many times. Data that aren't structured, like documents or natural language in, for example, emails or laws and regulations, and on and on. On top of that, oftentimes, the data that we're trying to model actually looks like a graph if we're just representing it without trying to fit it into a relational data model. Think of things like the power grid, relationships between people, right? It looks like a graph pretty quickly. Neurons in the brain, cities, the internet itself, etc. Now, all these common use cases where SQL doesn't really reflect business rules in a natural way has resulted in like dozens of SQL versus NoSQL articles. And to me, it's kind of a false dichotomy, or very rarely do we have data points that doesn't have any relation to other data points, which would then mean that they should be in a relational database or something like that. So honestly, I struggle a little bit with the SQL versus NoSQL debate a little bit, and find it more interesting to ask how graphs might give context to data, for example. Okay, so data platforms are trash and graphs are the new kids on the block. Not really, but if you're in the data space, like me and like we all are here, I think, you've probably heard talks about data mesh lately. Data mesh, the way I see it, is a new paradigm for data architecture, yes. Kind of like what the introduction of microservices was for system architecture. It's an architectural pattern for implementing enterprise data platforms in large, complex organizations that help scale analytics adoption beyond a single platform and a single implementation team. Or it's a suggestion for how to move beyond a monolithic data lake to a distributed data mesh. The following concepts are foundational for understanding the data mesh architecture. You have data domains, data products, self-service platforms, and federated governance. So data domains are the foundation of data mesh. The concept of data domains come from domain-driven development, a paradigm often used in software development to model complex software solutions. In data mesh, a data domain is a way to define boundaries around your enterprise data. Data products are another important component of data mesh. Data products aim to take product thinking to the world of data. So in order for your data product to be successful, it needs to provide a long-term business value to the intended users. In data mesh, a data product involves data, code assets, metadata, and related policies. And data products can be delivered as an API, as a report, a table, or a data set in a data lake, for example. A core of data mesh is having a platform that allows the data domains to build their data products on their own. They need the ability to define their data products by using the tools and processes that are relevant for their users without having a strong dependency on a central platform or a central platform team. In a data mesh, you have autonomous teams developing and managing autonomous products. So I hope you see like the microservices analogy here. And when you adopt a self-serve distributed data platform, you must place an increased emphasis on governance. Lack of governance leads to silos, which is what we're trying to avoid, and data duplication as well across your data domains. To create your federated governance, implement automated policies around both platforms and data needs, we must use a high degree of automation. We must adopt a code-first implementation strategy to handle standards, policies, data products, and platform deployment as code. Bringing it all together, it might look something like this. The data mesh platform is an intentionally designed distributed data architecture under centralized governance and standardization for interoperability enabled by a shared and harmonized self-serve data structure. So far from fragmented silos of inaccessible data. Now, does this illustration look familiar to anyone? If you ask, for example, where does the data lake or data warehouse fit in this architecture? Consider that there's simply nodes in the mesh, or should I say graph? So while implementing a data mesh won't necessarily give you or automatically give you a knowledge graph, as defined earlier at least, this to me really seems to be a fundamental shift in how we organize data, from trying to fit circles into squares with SQL to representing data with nodes and edges, aka relationships between the nodes. And I realized that I may have talked a little bit fast. This is, anyway, this is all I managed to pull together for now. I hope it pulled some sort of thread or made a connection for you from the idea of Semantic Web and RDF to the now emerging new ideas around data architecture like data mesh. That's really being pushed and driven by the shortcomings of SQL and growing needs for good and effective representation of data. The 2022 expectation of data platforms. So yeah, this is what I had, and thank you for listening in. You can find me my email here, Twitter, LinkedIn, etc. And yeah, thanks for having me, Confer.